what is, first of all, we should discuss what is electromagnetic spectrum should be seen. So we see that your electromagnetic spectrum consists of gamma rays, which is the highest energy radiation, which has penetration power, and it can bring about changes in the nuclear configuration. So if the nuclear configuration can be brought about, for example, it can bring about a mutation itself or change in the nuclear configuration, nucleus of an atom. Okay, X-rays. Now X-rays are like little lesser energy, but they have they are transparent to certain objects and opaque to certain. So they are used, as we know, in medical sciences to get the information regarding the bones and their fractures and all. But here in chemical analysis or chemistry, X-rays are very much used for determining the surface morphology and the phases, like the different phase material is there, like same compound but different phases. Their cubic structure is different. In such cases, you use it is termed as XRD, X-ray diffraction studies. Then you have X-ray fluorescence spectroscopy. Such methods of analysis are used in which X-rays are used. Yes, gamma rays are also used in chemical analysis. The method is termed as mass bar spectroscopy, in which the coordination compounds, like almost 50 coordination compounds, are uh, like dif- uh, 50 elements and their coordination compounds, the structure, whether it is octahedral or trigonal, bipyramidal, and that sort of information is obtained in mass bar spectroscopy. Then the next radiation wavelength of light is ranging from 3 into 10 to the power minus 7 to 10 to the power minus 8 meters. So that is ultraviolet radiation, and UV radiations, they can bring about excitation. Suppose if you are having such type of diatomic molecule. Now this is the atomic energy levels and this is the molecular energy level. So the ultraviolet radiation are capable of the energy of this light is capable of exciting an electron from the atomic energy level to the molecular energy level. Okay, whereas visible light, it is able to excite electron in the molecular energy levels only. So if you are having a sigma and pi bonds, now the pi bond being little weaker, we'll find that pi undergoes transition from pi to pi star. Here also pi to pi star or n to pi star. Such type of transitions can take place. Okay, so like this is the part where we use the concept of Beer's-Lambert's law, because this is the visible part and this is the um, ultraviolet radiation or ultraviolet region. So that is used, or the analysis is governed by Beer's-Lambert's law. Then you have infrared radiations. The infrared radiation are still lower in energy and they can bring about transition, not the electronic transition, but a transition in the vibrational energy levels. So you have, like if you see the energy profile diagram, the potential energy for a diatomic molecule like hydrogen, we know that every energy level, electronic energy level like 1, 2, 3, is associated with vibrational energy levels of equal uh, energy height, and they are represented by V. Okay, and electronic energy levels are represented by E, and each vibrational energy level will be then having certain rotational energy levels, so that comes in the microwave spectra. So vibrational energy levels are like if you are having dipole moment necessary. So dipole moment is very necessary for the infrared spectra. So if it is H2O or any such molecule where you have dipole moment, permanent dipole moment, then when it absorbs infrared radiation, there is a transition in the vibrational energy levels of the molecule. The vibrations can be, there can be like a scissoring sort of vibration, or bending up above the plane and below the plane, or you call it as rocking, like both the hydrogen atoms moving simultaneously on this side, and that's it. Let me see if some, yeah, this is a better. So this is a change in the vibrational energy level happens in your infrared radiation. So this is a molecule with dipole moment. So it may show like stretching vibration. So for some time it may go to this place. So it has stretched a bit, and it may come back. So that is termed as stretching, and the rest is like scissoring, rocking, bending, wagging, and all those type of transitions can be there. So it is only in the vibrational energy levels. Now, if the molecule is placed in microwave region, these microwaves are capable to change the rotation or orientation of the molecule, and that is termed as rotational spectroscopy or rotational spectra. Okay, so this is the rotation in the configuration of your molecule takes place, or the orientation of the molecule takes changes, and that is termed as rotational. Then you have electron spin resonance spectroscopy. Now this is all the radio frequency radiation. Is it written anywhere? Radio frequency. Now the energy of these radiation is very less. Now what is important now, it is seen in this region, the electron spin is inverted, or change in the spin of the electron is observed when you place a compound in this particular thing. And then NMR spectroscopy is obtained when there is a strong magnetic field. Okay, a magnetic field is applied, and under the influence of this strong electromagnet, when you place your sample in a test tube, you will find that the spin of the nucleus changes, and that is spin of the proton is changing. Now proton, what is proton? Now your hydrogen atom in a compound becomes the proton, and this proton, like you have H1, then C13, 15 phosphorus, such type of different NMRs are there. The simplest NMR will be proton resonance spectroscopy. Now the resonance is termed because like a proton which is spinning in clockwise direction, okay, in presence of a strong magnetic field. Now this magnetic field value is also uh, when it is in resonance with this particular thing, you will find that a proton which is spinning in clockwise direction starts spinning in anti-clockwise direction. So this is termed as orthohydrogen and parahydrogen. Okay, so we see that in such a case, when it is changing the spin, it is absorbing the radio frequency. Now this radio frequency radiation are of very low energy, but still they can bring about the change in the spin of the proton. Like if you are having a nitrobenzene, now what all hydrogen are there, they may show like some or you have ethanol or tertiary butyl alcohol is there, then all the H will show a specific peak for it, and that is termed as nuclear magnetic resonance spectroscopy or proton magnetic resonance spectroscopy. Okay, so this is how the electromagnetic spectrum is used in chemical analysis, and to find out various different type of chemical analysis can be brought about by using this light. Now, when you are using light for some excitation, like if you are having something at the ground level G0, it is going to a star level, that is the excited state level. So it is on either absorption of this, and when it is reverting back, it will emit out a certain radiation. So one thing is there, how much is absorbed by this particular atom. Either you measure that, what is done in your visible and UV region, the quantity of light absorbed by a colored solution is measured. So you get to know the concentration of analyte from the quantity of light absorbed. In some cases, it will be the quantity of light emitted, because if you are studying fluorescence, then maybe some UV light or X-ray light is used to excite, and then the emitted light is measured in fluorescence. So some fluorescent compounds you must be knowing, like your resorcinol, when you put it in water, it is fluorescent, then fluorescent, and so on. Okay, so this is the electromagnetic spectrum, and that is what is seen. Now, this is exactly reverse. Like here is your gamma radiation having high energy. The energy is joules per mole 10 to the power 9. Okay, and the frequency is 3 into 10 to the power 18 hertz, and the wavelength is 100 picometer, and wave number is 10 to the power 8. Now, we generally talk in terms of wavelength always. So, these things are important. So, in your UV visible region, you will find 10 nanometer to 1000 nanometer is the range of your spectrophotometer. Then the rest of the things are here, 100 micrometer, 1 centimeter, 100 centimeter, and so on. Okay, so we see that photosynthesis is due to absorption of this sunlight H nu, and it will help to fix the carbon dioxide into formation of glucose. Then you have a Grothus-Draper law. Only that light which is absorbed by the system can cause chemical change. So unless some light is absorbed, it can't bring about the chemical change. So it has to be absorbed first of all. So Einstein law of photochemical equivalences, each quantum of radiation absorbed by a molecule activates one molecule in a primary step of a photochemical process. Then this we already saw that the rate of decrease of intensity with the thickness of absorbing medium is proportional to the intensity of penetrating medium. The rate of decrease of intensity of radiation absorbed is proportional to the intensity of radiation and to the concentration of solute. And we had seen this part, if this is the intensity of incident light, then absorption takes place here. Part of it is absorbed, and the transmitted light is having little lesser intensity. And we see that uh, like you have to use a monochromatic light, that is light of single wavelength. When it is incident, depending on the thickness, your intensity of transmitted light will change. So that is the Lambert's law. When a monochromatic light passes through an absorbing medium at right angles to the plane of surface of the medium or solution, the rate of decrease in intensity with thickness of medium is proportional to intensity of incident light. In other words, the intensity of transmitted light decreases exponentially with the thickness of absorbing medium increases. So we had seen this in the practical part also, that log I0 by IT is equal to epsilon CT. So this is log I0 by IT, that is the intensity of incident light. This is the intensity of transmitted light. So this term becomes the absorbance. Epsilon is the molar extension coefficient, which is a constant. C is the concentration of absorbing medium, and B shown here is the thickness. Yeah, here it is written. Okay, so here epsilon is the molar extension coefficient. So A is equal to epsilon BC, and that becomes your Beers-Lambert's law. Okay, put together. So a double beam spectrophotometer. which is UV visible. So if when you say UV, the instrument should have deuterium lamp, so that when you put on the deuterium lamp or go to or you select the wavelength of UV region, this will be turned on. And for visible light, you use a tungsten filament lamp, and there is a monochromator, generally diffraction grating, which will give you single wavelength light which passes through the sample. Some part of it is absorbed by the sample and rest is transmitted. Whereas complete is transmitted here in your blank solution. So this quantity of transmitted light and this quantity of transmitted light, if you measure the difference between this IT, then you will get to know how much is the absorbed quantity. So this minus this value will be the absorbance. Okay, and that is what is measured by this. If it is a continuous one, like you get all the values for different wavelength, depends on your spectrophotometer, how the spectrophotometer is. So the wavelength at which uh, a colored solution absorbs maximum light is termed as lambda max, or wavelength of maximum absorption of light. Okay. Then we saw that T is equal to IT by I0. Percentage transmittance is 100%. So absorbance becomes log to the base 10 I0 by IT. So finally we write absorbance is equal to 2 minus log T. Okay. So a calibration curve is obtained which passes through the origin in such a way that it's a straight line, and at higher concentration you can see there is a positive or negative deviation. Now the limitations to Beers-Lambert's law are the linearity to the Beers-Lambert's law is limited by chemical and instrumental factors that are like deviation. Cause of non-linearity of the law occurs due to following reasons. So the first one is deviation in absorptivity coefficient at high concentrations due to electrostatic interaction between the molecules. So when the molecules are densely packed at high concentration, the interaction increases and will change the absorptivity coefficient of that particular substance. Then scattering of light due to particulates in the sample may occur. Then fluorescence or phosphorescence of the sample may interfere, or changes in the refractive index at high analyte concentration. I told you that day refractive index may change. Then shift in the chemical equilibrium as a function of concentration may be there seen, or electromagnetic radiation should be monochromatic. If it is not monochromatic, then again there will be deviations, and the solution should be dilute. If it is high concentration, then all these things will lead to deviation, and that is why it should be dilute. Then we have some numericals on this. The numerical is totally based on log I0 by IT is equal to epsilon CT. Either this formula will be used or some of these formulas will be used. They are one and the same. Okay. So only the numericals are based on your what you say, Beers-Lambert's law. Okay. So these are the numericals. You can take a picture of this. Answer is given to you. You can solve the numerical. Okay. Things are clear.
Yes, ma'am. Yes, ma'am.
Okay. So we will see the next portion, that is the organic reactions. Now I gave you this part for writing assignment, right? And I consider that everyone has read the three reactions which I gave you to write in your assignment part. So the first one is Beckmann rearrangement. The Beckmann rearrangement is named after German chemist uh, Arno Otto Beckmann. and it is a acid catalyzed rearrangement of oxime into an amide. So this is an oxime, and you get amide on treatment with sulfuric acid under heat condition. So most commonly used catalysts are concentrated H2SO4, HCl, PCl5, PCl3, SOCl2, zinc oxide, and SiO2. Okay, polyphosphoric acid also. So this is a general reaction of Beckmann. Then the mechanism comes here. So as you have already written the mechanism, I will not go into detail, but I'll share this PPT with you in PDF form so that although you have written the assignment, this will be there as a reference. Okay. So how the groups migrate and all. Then application of Beckmann reaction and Beckmann fragmentation and all. Then coming to the next one which I gave you was Hoffman rearrangement. So Hoffman rearrangement, this reaction is used for the conversion of primary amide to primary amine. So amide to amine conversion takes place in presence of NaOH and bromine. So Hoffman bromide reaction mechanism generally includes the use of an alkali as a strong base to attack the amide. Okay, so strong base is used to attack the amide part, leading to deprotonation and subsequent generation of an anion. Okay, so this is accomplished by heating the primary amide with a mixture of halogen, chlorine or bromine, and a strong base and water. Okay, so the mechanism and the reaction is illustrated here. Hoffman rearrangement, one by one, all the steps are mentioned here. So you can go through these steps later on. Then coming to Scrop synthesis. So this is Scrop synthesis. I'll go to this particular mechanism. This is Riemann-Tiemann. We'll come back to Riemann-Tiemann later on. Now, crop synthesis is a method to prepare a heterocyclic compound um, like your pyridine, furan, thiophene, oxazole. Crop synthesis is used to prepare quinoline from aniline. So first of all, the general reaction is your aniline when heated in presence of glycerol and or it reacts with glycerol in presence of sulfuric acid oxygen forming to quinoline. Now this process takes place in 4 steps. Okay, so one by one we can see the various steps that occur here. So crop synthesis is used to prepare quinoline and its derivatives, which have wide pharmaceutical application, like your anti-malarial drugs are all like pharmaquine, chloroquine, like they are quinoline compounds. So quinoline was first isolated from coal tar in 1834, and Scrop devised a synthetic method in 1880, this particular method. So aniline and glycerol were heated with concentrated sulfuric acid and a mild oxidizing agent like nitrobenzene to yield a quinoline. So ferrous sulfate and boric acid were used as moderators in this particular reaction that time. So the mechanism is, the first step is glycerol undergoes dehydration with concentrated sulfuric acid to give acrolein. So this is glycerol. When you heat it with sulfuric acid, you get acrolein. That is like you are having carbon formation of carbon-carbon double bond, and here, and the two H2O molecules are removed here in the first step. So the first step is conversion or dehydration of glycerol to acrolein. So the first step is acrolein. Now this is the acrolein which will be reacting with the aniline. So aniline goes and adds to the acrolein at this position, and you get an adduct 1,4 addition takes place, and an intermediate A is formed, that is termed as the 1,4 addition adduct. Okay, so like ring expansion is there. Then the third step is This 1,4 adduct compound or the intermediate A undergoes um, ring closure in presence of H2SO4 to form 1,2-dihydroquinoline. So you get formation of 1,2-dihydroquinoline by the ring closure in this region. Okay, and then the fourth step is 1,2-dihydroquinoline undergoes oxidation with nitrobenzene or ascorbic acid to get quinoline. This is quinoline. Nitrobenzene is reduced to aniline, which is reused. So this nitrobenzene, which is reduced to aniline, can be reused in the step two. Okay, so that is how scrop synthesis leads to formation of quinoline. Now here are the properties of quinoline. Now, what are the properties? It is colorless liquid at room temperature, melting point minus 19 degrees centigrade, boiling point 238 degrees centigrade. It undergoes electrophilic substitution under vigorous uh, conditions at C5 and C8 position, example nitration, sulfonation, then oxidation. It gives quinoline N oxide with peracetic acid and pyridine and 2,3 dicarboxylic acid with chem. Then regarding reduction, the reduction with H2 and nickel gives decahydroquinoline and with tin and HCl it gives 1,2,3 trihydroquinoline. Okay, so these are the properties, physical as well as chemical properties. Then coming to the application part, application, the most important application is 8-hydroxyquinoline is used as antiseptic and a laboratory reagent. Um, Antiseptics and laboratory reagents are synthesized by the scrop synthesis method. Then salts of quinoline derivatives are used as dyes, number of like dyes for number of staining of microorganism in microbiology lab, or or uh, staining of your fabric and a textile material. Okay, these find application in food colors also, like the food colors also. They are colored compounds, and thus such dyes are prepared. Okay, another application is naturally occurring substance found in the bark of cinchona tree is quinine. So you can prepare some such quinine synthetically by using this crop synthesis method, and you can prepare this anti-malarial drug called as quinine. Okay, this is the structure of quinine. So substitutes of quinine are manufactured again by crop synthesis, and they are plasmochin, plasmoquin, then tifanoquin, then chloroquine, and ataprin. Okay, so these are some of the structures. Like this is the moiety which is important, or you have seen its preparation. So this completes all your organic chemistry part. Okay, and I think Riemann reaction also you must have written, like conversion of phenol to orthohydroxybenzaldehyde. Okay, is uh, the Riemann reaction. Okay, so with this the organic part is over. Now we will come to polymer part. Okay, so things are clear. Is there any doubt? Yes, is there any doubt? No
No,
doubt
ma'am. No, ma'am.
regarding, yes,
No, ma'am.
no doubt
No.
regarding organic chemistry part. Only three, four name reactions are there that we saw: Beckmann, Hoffman, Rimmer-Tiemann, and crop synthesis. Okay. So some part of polymers I have given you as assignment. Now the remaining part we will see what are polymers. Like polymers, like mers means units. When you are having repeating units, it is termed as polymer. And these repeating units may lead to, if the chain length is very long, they are termed as high polymers. If the degree of polymerization is less, it is termed as oligopolymers. So common use of polymeric material is shown here, that is packaging bottles, surgical sutures, electric components and contact lenses, adhesives, then medical supplies, bone cement, then blood bags. They are all made up of polymeric material. The number of polymeric materials are also used in paints, automotive parts, where housewares, then Tupperwares, plates, cups, fabric, rubber, pipes, plastic bags, and so on. So this is the photo of the utility of your polymers. Okay. So the word polymer is combination of two Greek words, poly and many. Mers means parts. So that is how ethylene, like ethylene should be shown with a double bond necessarily, because without having functionality, you can't go for polymerization. Unless one of the pi bond will break, it will not make this part available for polymerization, right? So monomers give polymers and they are of such type. So you generally write it n times like this, and that is how they are represented. The polymers have low density, low coefficient of friction, good corrosion resistance, good moldability, moldability, and then excellent surface finish can be obtained. It can be produced with close dimensional tolerance. They are economical, poor tensile strength, low mechanical properties, poor temperature resistance, can be produced transparent or in different colors. So you can make it more lucrative by putting certain dyes into it or color into it, and you can use it. So polymers, some natural polymers are there, some synthetic elastomers and synthetic polymers. Now, natural polymers are like your cellulose derivatives. Now, you must have seen um, cotton uh, growing on a cotton plant. The the cotton balls, when they mature, white cotton, so that is a cellulose thick material, and the cotton fiber, every one of you have seen. So every fiber is a polymer of cellulose, and that is how the cotton fiber is a natural fiber. Okay, natural polymer. Then you have gelatin, waxes, proteins, gum, different type of gum, shellac, natural rubber that is obtained from the trunk of the rubber tree. Okay, white latex, sticky white milk is obtained, and then when you treat that with acid, it gives formation of a white coagulated solid that is used as rubber. Starch and chitosan. These are natural polymers. Then synthetic elastomers, uh, hydrogen rubber, silicone rubber, nitrile rubber, acrylonitrile, and neoprene rubbers. They are all rubbers come under the class of elastomer. Now, what is the peculiar feature? The molecule is something arranged in such type of thing. So they are the molecules, since they are arranged like this, why they are called as elastomers, because they show resilience and rebound, as well as when you stretch it, it will become such long. So the whole molecule then becomes such long, and this part is able to uh, this is the entangled snarls, which become straight when you apply some stress over it. Okay. Then synthetic polymers like polyvinyl alcohol, PVC, then polyethylene, polypropylene, polyamide, polyurea, epoxy resins, and so on. Then classification of polymer. Now classification is done based on the source or based on its structure, based on the molecular forces, or based on the polymerization, that is way of polymerization. So very first see one we will see is uh, natural polymer, semi-synthetic polymer, and synthetic polymer. The name indicates what they are. Then linear polymer if the molecule is straight, branched polymer if you are having branching on the sides like certain functional groups are there and branching is there, and a highly cross-linked will be something like this. Okay, so a highly cross-linked or three-dimensional polymer is another type. Then you have elastomers, fibers, thermoplast, and thermosetting polymers. Then based on the polymerization, you have addition, polymerization, condensation. So the example I think are there further. What is addition and what is condensation, polymerization, that should be seen. This is something like classification based on source, then natural polymers, and this natural proteins and polysaccharides. Okay. Now here we see natural polymers. If you see in detail, you have some proteins, albumin, fibrin, collagen, and then polysaccharides like dextran, chitosan, starch. So they are different type of natural polymers. They are non-toxic because they are natural. Generally, it is seen that they are non-toxic in nature. Then cotton, a natural polymer is these are the balls, cotton balls, and this is the image of the cotton fiber. Then rubber is obtained from the bark of the rubber tree, white liquid, white milk, and that is then collected to give you natural rubber. Now, natural rubber, when this is there, it is the isoprene unit 1, 2, 3, 4, 5. Okay, so this is the isoprene part. Now, in this case, there won't be this double bond, it will be here and here are the double bonds. So, this is only a single bond. So, when you treat it with acid, you get the polymerization of isoprene and leads to formation of this type of structure. Okay. Then your DNA, a nucleic acid, is a polymer, deoxyribonucleic acid, where you have adenine, thymine, pentose sugar is there, uracil and guanine is there. Okay, and then primary structure, then peptide chain of amino acid. This is the peptide chain. You must be know CONH is termed as the peptide linkage. CONH that actually पहले कंडेंसेशन पॉलीमराइजेशन का एग्जांपल होना चाहिए. Adipic acid and hexamethylene diamine. Why synthetic polymers? Man-made synthetic polymers. So these are some of the man-made synthetic. Why synthetic polymers? Synthetic polymers are strong and light, can be made to have properties, then they are cheap, resistant to corrosion, and can be remolded and molded easily. Then environmental pollution resulting from disposal of synthetic polymers. So that is a different hazard. Now is the important part that can be asked, like linear polymers, then you have branched polymers, then cross-linked and highly cross-linked three-dimensional network. Then you can have a homopolymer and a copolymer. Copolymer can be a block polymer, graft polymer, alternating and statistical. So that is the example of homopolymer. All the repeating units are of the same type, whereas in copolymer, the repeating units are of different type. When you talk about block, there are blocks of one type, then another type is there. So this is how they are arranged. So the examples for this is polyethylene, where same type of this thing is there. Then a copolymer in which you have like styrene, butadiene, rubber. Now, I did I give you styrene, butadiene, rubber in your assignment? Was it there?
Yes, ma'am.
So what was the ratio? Some 25% of one compound and 75% of another compound is taken, right? So you are taking in 1:3 proportion. So that becomes a copolymer where you have one molecule and then three of one type and then again one. Isn't it? आपने लिखा है assignment तो अभी आपको पता है. Okay, so that is an example of copolymer. Then grafting. Now the polyisoprene, that is rubber. Okay, natural rubber. Now when you add sulfur during vulcanization of polyisoprene, sulfur is added at these sites where the double bond is there. So two sulfur atoms will be added and the lower chain will be there. So that is termed as vulcanized rubber. So on vulcanization, you get an vulcanized rubber, which is used for preparing the tires of automobiles, and an ebonite is one with 32% of sulfur in it, and that is used to prepare the tires of aircrafts which find a lot of abrasion and um, erosion due to like when it is landing, especially during landing, a huge impact is there. So such type of ebonite or the vulcanized rubber is used for which is very tough, and like here it is shown vulcanization. This is your isoprene, polyisoprene with sulfur under steam and this thing you get formation of such grafting is done between two linear chain. That is why this is an example of graft polymer. Okay, so if examples are asked, you can write vulcanized rubber as the example of graft polymer. Then addition and condensation polymerization. So isoprene is this like with two double bonds, um, and it gives formation of like this bond will break, and during polymerization it will make available these two. Okay, and this will shift here. So that is what has happened, and this line should come out of the bracket. So that is how you prepare um, addition polymer, that is natural rubber. Then coming to chain growth polymerization addition process. So free radical initiation process is there, cationically initiated process is there, then anionically initiated process are there. So your initiator will be different, like either free radical, cationic compound, anionic compound. So and we have seen that an initiator is necessary because it initiates the reaction, and then once the uh, chain initiation takes place, then chain propagation is the second step, and then chain termination is the final step. So that gives you either oligopolymer or high polymer. Okay, so here we see how this particular um, radical is transferring its like is reacting with styrene and is producing like like this pi bond will break and the radical will be joining here, gets attached to this, and this part, the radical part free to form bond is here. Okay. Then condensation polymer, as I told you, this is a very good example. You have adipic acid, okay, and hexamethylene diamine. So this removes one H2O molecules. So a small molecule like H2O is removed, and you get formation of CONH, a peptide linkage. So this is a nylon 6,6 because 6 carbon on this side and 6 carbon are here. So this is nylon 6,6, and you know the application of nylon 6,6. Then another example is the bisphenol A with phosG. Okay, so in this case, we find removal of, instead of water molecule, now there is removal of a small molecule like HCl. Okay, here it was H2O. So you get formation of polycarbonate polymer. Then polyester and polyamides. Polyester and polyamides are example of condensation polymers and are formed when a carboxylic acid monomer reacts with an alcohol monomer. Okay, so when you have an carboxylic acid, this is the carboxylic acid monomer reacting with an alcohol monomer, you get removal of H2O from the moiety, and the mm, polyesters are formed. Then polyamides like nylon and Kevlar are formed when the amide link is formed by the reaction of amino functional group with the carboxylic group. So you have COOH group and NH2 on this side. So a water molecule will be lost from here and you get formation of an amide linkage. Okay. Then condensation polymerization. In step growth polymerization, a linear chain results from the stepwise condensation or addition of reactive groups of bifunctional monomers. So we see that polyesters, polyamides, and polyurethanes, such kind of compounds are formed. Like this is your A part, this is your B part. So it gives formation of this such type of compound. Okay, on the basis of tacticity, like was once upon a time a favorite question. Classify and give example based on the tacticity. Tacticity is something like how the groups or the functional groups are attached to the backbone. You have a linear chain of the backbone. So if the functional groups are arranged on if the side groups of the monomer lie on the same side of the chain, it is called as isotactic. If they are alternating on both the sides, then it is termed as syndicotactic. And if it is randomly arranged in an irregular fashion, then it is termed as atactic polymer. So the diagrams are shown here. So this is an isotactic polymer where you are having this functional group on one side only of this linear chain. But if this R is on the other side and this is on this side, so this becomes um, syndicotactic. Like every time it is uh, like alternating, like one on that side and one towards you, one away from you and one towards you, one away from you and one towards you, like so this is syndicotactic. Example of this is gatta parcha rubber. And the example of isotactic is your PVC. Okay, then atactic is polypropylene, mostly polypropylene, but polypropylene also, depending on the polymerization condition, may be atactic, isotactic, or syndicotactic. Now, plain representation of polypropylene polymer. Now, isotactic polymers, um, they are on one side only, the methyl group. The functional groups on same side of the main carbon skeleton, they are isotactic. Then, if the groups are alternating on the two sides, then it is termed as syndicotactic. And if they are randomly arranged, sometimes on this side, sometime on that side, then it is atactic polymer. Then coming to highly regular and crystalline polymers, then irregular and amorphous polymer, and semi-crystalline polymer. So it is seen that these are the examples which show, like these are polystyrenes only. Now polystyrene with such a structure will be crystalline, this will be amorphous, and this will be semi-crystalline in nature. So polystyrene is atactic, polypropylene is largely isotactic, PVC is largely atactic, and polymethyl methacrylate is atactic. So these are the examples of these polymers. Okay, so for today we will stop here and we will continue tomorrow with rest of the classification and structure property relationship. Okay, so tomorrow morning we
Ma'am,
have a class 10 a.m.
ma'am,
That time we will complete the polymer part and what is remaining coordination chemistry. So I most probably by tomorrow we will be completing whole of the portion. Okay, and if you have any doubts, please write it in your notebook and tomorrow morning we will discuss all those doubts.
ma'am, will you send the PDF of my origin also?
Yes, PPT.
Yes, ma'am, corrosion.
Okay, you want PDF of the PPT slides of corrosion.
Yes, ma'am.
Okay.
Yes,
Okay,
ma'am.
I'll make PDF of like see organic I am going to make, but that is not also complete. Like a number of things like you have to write. Without writing, only writing reaction, no one will give marks. But the PPT is made like that, but still like we have to go with this. So you have to write the in sentence form also what exactly is happening. Okay, I'll give you all those things or I'll put it in your group. Okay, polymers also I'll put.
Okay.
Okay.
Okay, ma'am. Thank you, ma'am.